Hello everyone. Let's continue our discussion on deriving the equivalent circuit for a CMOS inverter. So we were actually supplying some varying boundary conditions to this CMOS inverter and trying to derive an equivalent circuit out of it. So the reason we are doing all this is because we need an equivalent circuit for a condition where Vin is high. We need an equivalent circuit for a condition where Vin is low. We'll try to merge those two circuits, okay, and try to derive the VTC or the voltage transfer characteristics of this CMOS, and that will be eventually used to evaluate the delay of any cell. In this case the cell will be an inverter, so it will be used to evaluate the delay of the cell of an inverter, but the same concept will be used to derive the delays of any cell of an AND gate or OR gate or any kind of gates. So that concept will be used, so this concept will be used to derive delays of those cells. Okay, so that's the reason we are doing all this. So next what we'll do is we'll take a different condition where your Vin is low, and is equal to 0 volts. In this case what happens, if this is your Vin, this is your VDD, we assume it to be 5 volts. So your gate to source voltage, which is from this point to this point, for PMOS it becomes 0 minus 5, which is negative 5 volts, and that will actually turn on your PMOS. Okay, and the reason is the gate to source voltage for your PMOS is expected to be lower than the negative VGS should be less than negative VT, and the reason for this is because of all the polarities of the voltages. Eventually when you take a mod of all of them, as we had discussed in the last videos, it becomes all in the same range. For a transistor, for a MOSFET, it becomes everything the same. Just because of the polarities of PMOS and NMOS of the voltages, the condition arrives to be something like this, which says that negative VGS should be less than negative VT for a PMOS to be turned on. In case of an NMOS, it should be positive VGS should be greater than positive VT for this thing to turn on, which was the case in the previous boundary condition. Okay, so in this case your negative VGS is greater than the less than the negative threshold voltage of PMOS, which says that the mod of VGS is greater than the mod of VT, and as a result of that your PMOS turns on. Okay, and the other case where you have your and we also know that to represent a PMOS or to represent an on transistor, we use a resistor. Okay, so whenever there is a direct flow of current from one point to other point, the wires are not ideal, and I'll be coming to wires in a bit from now. The wires are not ideal. They will have some finite resistance because the wires are physical wires, which has got a width, depth, length, everything. So it has got a resistance, and we will represent that thing with an RP, a resistance of the PMOS transistor. Rn was used to denote the resistance of NMOS. RP is used to denote the resistance of PMOS, and very soon we'll be proving that this resistance is a non-linear function of your drain current. Okay, so we'll be proving, we'll be coming. So this is not a regular resistor that we will be using. It's a non-linear function of your drain current. Usually if you go by the Ohm's law, it's V equal to IR, where your resistance is a function of your is a linear function of your voltage, but in this case it is not. We'll come to that part in a bit sometime from now. Okay, so in this case where your Vin is low, your PMOS gets turned on, and it can be modeled as a resistor. Okay, similarly in this case when your Vin is low, this is 0 volts, this is at 0 volts, your VS is at 0 volts, so your gate to source voltage for your NMOS is 0. 0 is less than threshold voltage, so your NMOS is off. Your NMOS turns off, and to represent an off transistor you just need a switch which is open. Okay, in this case the switch is open. So we have everything what we need till now, and we will be just trying to conclude things over here because this is still in an ad hoc manner. We'll try to do something very systematically. So let's try to do that. Will the output load capacitor is put over here. So we'll remove the transistors present over here, and we will try to focus only on this one. So this says that, let's try to bring it up. Okay, so this one says that in a case where your input voltage is VDD, this is what your circuit looks like. Okay, when your input voltage is 0, this is what your circuit looks like. So we have looked into the voltage conditions till now. But what about the currents? We need to find out the currents as well, because that's what is going to determine your voltage transfer characteristics eventually. Okay, so we need to identify how does the currents look like. So let's do that. So when your Vin is equal to VDD, there is a direct path that exists between V out and VSS. And how is it so? It's something like this. So there is a path from V out to VSS, and as a result of that you will see the V out to be 0. So basically, if your capacitance was completely charged, okay, if your capacitance is completely charged, because of this particular scenario, or the condition which is V in equal to VDD, all the charges which is present in this capacitor will discharge through this particular Rn, or the NMOS resistance, and as a result of that, the voltage, the potential at this point will be completely 0. Okay, so we have an additional voltage or additional potential to be found out over here, which is V out equal to 0. So when V in equal to VDD, V out equal to 0, we will be drafting it in a very systematic way. For now, we are just texting it over here, where V in equal to VDD and V out equal to 0. Next you have, so we are just drawn the direction of current, and it's very important to notice this direction of current. I'll come back to the direction of currents in a bit from now. For now, you have your V out equal to 0, and the reason, because all your capacitor discharges, because there is a direct path exists from this capacitor to the ground. Okay, the next condition where your V in is equal to 0, in this case there is a direct current flow from VDD to the capacitance. So let's say your capacitance was completely discharged, and as a result of that, the V out was 0. But with this input condition at V in equal to 0, you will see a direct current that flows from VDD to this capacitor, and thereby charging this capacitor under this condition. And as a result of that, you see as V out equal to VDD. So V out, the voltage across this particular capacitor will just match with what you see at the output potential. So your V out will be VDD. Okay, so these are few more conditions, and the direction of the current flow is what is shown over here. Okay, so there is a very important thing to notice for the direction of currents. I'll come back to that in a minute. Before that, let's try to summarize what we just learned. When V in equal to VDD, your V out is equal to 0 because of the direction of currents. When V in equal to 0, your V out is equal to VDD because of a similar direction of current, but it leads to the complete charge of your output capacitor. Okay, so what the next part is is the naming convention. We just need to give some names to these nodes, because eventually we'll be writing a spice circuit for this one, and therefore we need the node name. So let's try to do that. We'll call this as, this is the gate. Yeah, this is the source, this is the drain for PMOS, and again gate, drain and source for PMOS, and their respective connections. In case of a PMOS, the source is connected to VDD. In case of an NMOS, the source is connected to ground, because of the potentials and the way the electrons or the holes behave in case of PMOS and NMOS respectively. So that's the reason. Okay, from this observation also we need to add some more naming conventions. For example, this is called as VGS, this is also called as VGS, but just to differentiate between PMOS and NMOS, let's call this as VGSP, let's call this as VGSP, and let's call this one as VGSN, just to differentiate between the NMOS and PMOS. So P represents PMOS and N represents NMOS. VGS your gate to source voltage. Okay, so just for the representational, we are using two different naming conventions. The meaning of both is the same, but one is in the NMOS perspective and one is from the PMOS perspective. Okay, so moving on, we need to add some more conventions. Let's call this as VDSN. VDS is your drain to source voltage, and N is for the NMOS, and VDSP, which is your drain to source voltage for your PMOS. So we are just given two different naming conventions, and the reason for that is we need to use both of them together in certain equations. So that's why we have given two different names. Okay, and some more naming conventions. We need to see what is the direction of this. We need to see the naming convention of this currents as well. So let's call this as IDSN, the drain to source current through the NMOS, even though your PMOS is off and your NMOS is on. But let's try to give a name, because this is the current that flows through your NMOS. So let's give this a name as IDSN, and let's give this as a name as IDSP, the drain to source current flowing through PMOS and the drain to source current that is flowing through NMOS. Okay, So with that said, we with the naming conventions, what we'll do, we'll try to derive some equations. For that, we would need to get into deeper values of VGSP, VGSN. Basically, what we have to do, we have to derive what is VGSN. In this case, VGSN is V in minus VSS, VGSP is V in minus VDD. So we'll need to learn those explanations. We'll need to derive some equations. So that will take a bit amount of time. So let's try to come up with those with the videos on the explanation of the derivation, and try to derive the load curve, or try to derive the voltage transfer characteristics curve for your CMOS inverter. Let's try to do all this in the next video. Thank you.